Hello. Now we are going to speak about the nature of sound, and we'll speak about the part that is that concludes the first chapter, which is part 3. So these are the concepts that we are going to speak about: absorption, reflection, refraction, diffraction, interference, frequency and pitch, and then the decibel scale. And then there are some videos that I'd like you to view. So first, in order to understand what absorption is, we need to understand what an incident wave is. So an incident wave simply is a wave that, as it travels, it hits a barrier. That's it. It doesn't matter what happens next. It is just if that wave is traveling and there's a person that it, for example, it hits, or a wall or a chair, anything. It's a wave that hits a barrier, an incident wave. Now we'll see what happens. So that wave, when it hits the barrier, it may be transmitted through the barrier, it may be absorbed by the barrier, or it may be reflected back either completely or partially by that barrier, depending on the quality of the barrier. So the reflected part of the wave, it travels in the opposite direction as you see in the video, and it travels back to the source of the sound. So that is called sound reflection. Absorption behaves exactly in air. Absorption of the sound waves is exactly similar to absorption of of water or any liquid. When you have a napkin like this, and if you put a few drops of water on a surface and put this napkin on them without pushing or anything, gradually the spaces, the holes inside of this surface of the napkin are going to absorb, take in the water. The water will not disappear when it goes away from the desk or the surface. It will be here. So different things absorb based on the characteristics, on what they are made out of, and so on. So in sound waves, when we speak about sound waves and how they are absorbed, sound waves, when they're partially or completely absorbed, we call this damping. So absorption is the dampening or damping of a wave because of increased friction. The extent to which a wave is absorbed is going to depend on the nature of the surface. For example, again, it acts similar to the way that fluids are absorbed. If you have a sponge, what makes the sponge an absorbent surface, is the fact that it has a lot of air space inside between the molecules. So if you have a sponge, like say big sheet of spongy material, and you cover an entire wall or an entire room with the spongy surfaces, you are going to speak there, your voice will be very dull, because a lot of the air waves that you make are going to be they will travel and they will be embedded into the surface of the sponge, and that nothing is going to go back. The sound will be very hard to hear. So in the meantime, if you have a surface like a wall that's very shiny and very smooth and has no holes at all, then you speak, your sound is going to echo. It's going to be vibrating back to you, and that could cause a problem in the meantime. So there has to be a medium, there has to be a way in between where the sound wave is not completely reflected to you or to the source, and it is not completely absorbed. It's a science. So the classrooms that you have your classes in, they are tested for sound quality. They are tested for absorption and for reflection, so that they do not, create reverberation, and they do not create too much absorption, and they will be optimal this way for sound transmission. So soft surfaces that have pores in them, surfaces that are rough, are going to absorb more of the sound wave than surfaces that are smooth and dense and have no holes. So now sound reflection. We said an incident wave is a wave that hits a barrier. That's the definition. What is sound reflection? From that point that the wave hits the barrier, then the part that is reflected back, if the whole wave or part of the wave is reflected back, that is sound reflection. So reflection is the bouncing back of parts of the wave that are not transmitted or absorbed by the barrier. So again, hard and dense and smooth surfaces that do not have any holes, they are going to reflect a lot of the wave. Do you ever wonder, when people go to concerts, sometimes they wear these shiny dresses and shiny suits? I mean, have you ever wondered why? In auditoriums, there's a large space, and when you make a sound, when you say singing or a band, the sound is coming out. As it travels, it hits people. People are barriers. It hits their hair. If the hair is very smooth and it's not curly and fuzzy, that hair is going to it's not going to absorb as much of the sound wave. The clothes you are wearing, if you are wearing shiny clothes, polyester material and stuff like that, that is going to reflect a lot of the sound wave that is being played. If you are wearing wool sweaters that are fluffy and kind of fur, have a lot of fur and all of this, that would absorb lots and lots of the sound wave. The sound will be dull, and the person would have to raise their voices so that they could be heard, but the sound would not be rich. So you notice, look for when people are going to these events and see what kind of things that they are wearing, very shiny, very kind of, sometimes you say, it doesn't make sense, to wear these things, but that there's a reason that some people know, some people do not know. Sound, how it travels. It travels at a constant speed for any one of us on Earth. We know it as the speed of sound, and we defined it before. And we said, at sea level, at freezing temperature. And of course, once you increase the temperature, you are going to have, change the rate of sound travel. So sound travels faster in hot air in the summer, for example, than in cooler air. That is because air molecules, each molecule has a sphere around it, has like a space that it doesn't want any other air molecules to invade. And the colder the temperature is, the smaller that space is for the molecules. So when the air, like when it was cold, and my balloon, my birthday balloon that I had, the air molecules huddled together. They did not require a lot of room between each other. So when you heat when you raise the temperature, air molecules tend to spin faster. By doing so, they want to have a larger space. And the higher the temperature is, the greater the space that they would like, because they're going to be spinning back and forth and going really fast. As a result, if you raise, every time you raise the temperature by 1 centigrade, I told you 0 centigrade equals 32 Fahrenheit. So if you raise the temperature by 1 centigrade, you are going to make the sound travel faster by 0.6 of a meter. For example, if you have someone, in the winter, you are going to call someone and it's freezing temperature. The sound is going to take if that person is standing at 331 meters away from you, and you call their name and say hi, the distance, the sound is going to travel in a single second between you and the person who is standing at 331 meters. So now, in the summer, in order to make that sound travel, if the person is standing 330 meters, 330.4 of a meter, then that will take 1 single second. So you decrease the distance by 0.6 because the temperature was raised by 1 centigrade. And of course, when you say if the temperature in the summer is, maybe 23 degrees, which is equal to 98, something like that. Every time you add 1 more centigrade, you are going to make the sound travel faster and faster and faster. And you can calculate it definitely, but we don't have to do that. Refraction. When you have a container, like say water, you can do it now. You get a glass of water and put a fork in it or a straw in it. Do you notice that when you look at it, it looks as if that straw is broken between the line where the water ends and the air begins. So it looks like that, straw or fork is broken. And the reason is the difference in temperature between the air temperature and the water temperature. The water temperature is cooler, so the contrast causes refraction. In air, refraction is a change in the direction of the sound wave because of the temperature change. So, for example, in the day, the surface of the ground is hot. And the air, as you go up, the air becomes cooler and cooler and cooler. So you end up, you make a sound, the sound is going to deflect, go up in the direction of the warmer air. But then there's a pocket, there's the warm air makes like a pocket, and on top of it there's cooler air. So the sound is going to travel through that hot pocket and then it's going to come down again, to the ground again. The best example, it is explained in the textbook. When you have a lake and you have on one side of the lake someone is saying something, on the other side of the lake someone is going to hear that. And that's a phenomenon that at night in particular, you hear, like, I used to go fishing near lakes and stuff, and it would be very quiet at night, and then you hear like a couple of miles away some people are talking on the other side of the lake, at night. And in the day, you don't hear that. And the reason is that the earth, the ground has a high temperature. The water has lower temperature. This is why people like to live near lakes and stuff. It has cooler temperature. And then, especially at night when there's not a lot of noise and stuff, you look at the lake, the air on top of the lake, because it's cooled by the water, is going to be cold. And the higher that, the closer it is to the center of the lake, the colder the air is. So you have like a dome, where the air acts like a dome. The closer you go to the shore, the less the hotter the temperature is, until you go to the ground, and then it is. So it acts like a dome. So the sound on one side of the lake is going to travel and will be deflected through in the direction of the hot air above the lake. So it's going to travel and it will be reflected back to the other side. So it's going to travel in a more enhanced way this way. And you can read the description in the textbook. And then sound diffraction. Diffraction, when you say diffraction, you create many copies of the wave. So sound diffraction is the change in direction, the direction of the wave that is traveling through an opening or around an obstacle. So the greater the wavelength is, the greater it diffracts. For example, if I want to, I create a hole, and as I'm speaking, the sound is going to, it's not just going to go through, straight. No, it's going to go like in different directions, like this, up and down, and fanning in different directions. And each time, it makes many copies. And this will add up together to make the sound louder, because that will be similar to the way we combine pure tones. So this is one of the reasons, for example, that when you go like that, you have a hole here, and you say, ooh, that is going to cause the sound to diffract, and you create a megaphone. So this is exactly how the thing works, through sound diffraction. So again, the definition is the change in the direction of the wave that is traveling through an opening or around an obstacle. Like if there's a wall, the sound is going to hit it, and then it's going to diffract up. And the greater the wavelength is, the greater it diffracts. So for this reason, for example, adult male voices can travel in, through the edges of a room, and can go to the, exit to the next room easily because of diffraction. Like the door is open, it has a hole, and then the sound wave comes and hits, that area, and then it diffracts out, so you can hear the person in the next room, or in another room. The sound of the concept of interference. Interference, it is not all good, it's not all bad. It could be either or, depending on the type of interference. So when you combine two sound waves, when you play them exactly at the same time, it depends on if the two sound waves are pushing in the same direction, or if one is pushing in one direction and one is pushing in the other. How do you know that? think about sound waves as the waves in the ocean. One wave, you have a peak, rises, and immediately you have the trough, the water lower, going down lower. And then you have another wave, and another wave. If you have two waves where the compression of a wave aligns with the compression of the other wave, both of them are going to push in the same direction. Both of them will add their energy together to create a louder sound. So that is called constructive interference. And that enhances the sound by making it louder. It gives it a higher amplitude. Even if this wave, as the example that we discussed in part 2, when you have one wave that is twice as long as the next wave. So the parts of the big wave that coincide, the compression part that coincides with the compression part of the second wave, both of them push in the same direction, both of them are going to add to the loudness of the wave. And the parts where compression of a wave contrasts or meets with rarefaction of the other wave, when they meet each other, they cancel out each other. So you have one rarefaction that doesn't have as much energy in it, as much pressure in it, coincides with one part of the compression of the other wave. As they go down, that piece of the compression is going to be absorbed. It will fill that gap in the rarefaction, and that will delete a piece of each wave. That will be called destructive interference. And each one can be partial or can be complete. So let's see. Now, we have one wave, the blue wave, and we have another wave, the red wave. Are they pushing in the same direction? In other words, is the compression of the first wave pushing in the same direction as the compression of the second wave? The answer is yes, even though they are not perfectly under each other. So that means that they are played, the top one is played first and the second one is played before the top one ends. So you end up having this part here, this corner of the blue wave coinciding with this part of the red wave here. So that little corner here is going to be added up. So whatever coincides together, that part is pushing at the same time with this part, and that is going to raise the amplitude or the loudness of that part, because now you are combining them. So you end up deleting, the thing doesn't get to go to rest now. So that area here is deleted because you added, this part of the compression with this part of the compression, and you increase the sound by, say, 1 decibel or so. That means it doesn't come to rest, and you create a whole new wave that looks like this. So let's now look at the one below. The blue wave here has a compression, and the red wave now is in the rarefaction mode. Rarefaction has lower pressure, compression has higher pressure. When they are played, the part of the compression of the blue wave coincides with this part here of the red wave. So as this red wave is moving toward rest, and the rarefaction of the red wave is moving back to rest, they hit each other, and there's a gap in there in the red wave that will absorb that part of the compression of the blue wave, and that part is going to be cut out of the blue wave, and that part that coincides with it will be cut out of the red wave, and you end up having a new wave that is now smaller. It has a shorter wavelength than the blue, and it has a shorter wavelength than the red, so that now you created a higher pitch, a higher frequency wave by combining these two together through this partial destructive interference. You cut out one piece, deletes another piece, and then you end up with a shorter wavelength. So now let's see how these things work out in more detail. Here's a wave, wave A, and there's wave B. Let's see if they're the same wavelength. You can tell by, if you make a line here at the end of this first wave, and you just go straight up, you're going to find that this is the same wavelength. This wave exactly is the same wavelength as that. If you get a ruler, you're going to find it this way all the time, all of them. So now they play together. The compression of the first wave coincides perfectly with the compression of the second wave. So both of these, they push in the same direction. As they go back into rarefaction, the rarefaction of the second wave pushes in the same direction as the rarefaction of the second wave together, and that in both cases doubles the amount of energy, it doubles amplitude or loudness for both. So, but in the end, you get a single wave out of these two because they are perfectly the same in everything. So now you get a wave that is twice as loud as both, either one of these waves. So if this one is 1 decibel, this one is 2 decibel because it added 1 plus 1. And then you get this new wave that is louder. This is again like two people singing. If you have one person singing at a certain volume, and then the second person sings at exactly the same volume, given that both of them have exactly the same fundamental frequency, the sound will be twice as loud. If all the class starts singing and all of the class have the same exact, similar voices, then the sound is going to be as loud as all of us. And this is why the idea of a chorus, they get people whose voices are very, very similar to each other, and they have them play exactly at the same, time, saying the same things, and their voices become as loud as the group and all. Okay, now let's look at this second example. We have wave A is, the wave that has the trough here is A, and it goes up, and it's gonna be here. I'm sorry, it goes up here, the one that's in the middle here. That is wave A. Down, 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 and then here. Wave A. Wave B is the smaller one below it. Wave B here. Here. I mean, they are the same really in terms of wavelength. They're exactly the same wavelength. They are exactly the same. They take the same time to finish. They are exactly the same frequency. The only difference, what is the only difference between these two waves, A and B? The difference is loudness. The difference is that one is twice as loud as the other, which is wave A is twice as loud as the other one. So when these are played together exactly at the same time, compression pushes in the same direction as this compression, rarefaction in the same direction as this rarefaction. You end up having, they add up into that red wave that will be the wave that is the result of A and B. and no more. You are not going to have any more A or B. You're just going to have that red wave. That is the outcome. So that is what kind of interference is that? I hope you can answer this question. I'm not going to answer it now, but if you are confused about it, I will be happy to clarify in class. Now we have another scenario. We have a wave A. That wave that has a it has a greater amplitude than the other wave. So wave A is about twice as loud as wave B. However, wave A is played in a way to make the compression of wave A coincide with the rarefaction of wave B. So whenever you have a compression and a rarefaction, they absorb, and the rarefaction absorbs the compression. If they are equal, if they are exactly equal in loudness. So now we are not equal in loudness. Wave A is twice as loud. So wave B, the rarefaction is going to absorb as much as it can, and what is left over because of that excessive, that area between the red line and the black line, that is the excess. That is the difference in loudness between wave A and B. So wave B is going to absorb 1 decibel of wave A, and then what is left will be 1 decibel. So that is the red wave. That is going to be 1 decibel. And no longer, you are not going to have any, B or A after that. You're just going to have that red wave that is resulting, and it will be just a single decibel. Okay, so what do we call this? We call it partial destructive interference. The second one. The first one, we call it we call it complete constructive interference, because you do not lose any energy here. You add up the energy. Reverberation and echo. The difference between them depends on when the wave reaches the eardrum. So, in reverberation, you have a wave that travels, hits a barrier, is reflected to the source. Like I'm speaking, my sound wave is hits the end of the desk that I'm using to record, and then it comes back again to me. So that reflected wave, it arrives at the tympanic membrane at the eardrum slightly after the original wave. Original wave, I make a sound, leaves me, goes to hit the barrier. As it comes back, the eardrum, my eardrum, is still vibrating in response to the original wave that I made. So before that vibration stops, the second wave from the reflection is going to come in, and it will continue vibrating my eardrum. And I do not feel a difference. I feel as if there is no, that it is one sound, because it was vibrating, and then before it stopped vibrating, this other wave came in and picked up, and it continued. So reverberation makes the sound longer. However, it is a single sound that you hear. And it's very important to say that it arrives, the second wave, the reflected wave, arrives at the tympanic membrane, or hits it while the tympanic membrane is vibrating in response to the original wave. Because the second wave is an echo, is a copy of the original wave. So the level of the reverberation depends on how far you are from that barrier. The closer you are to the barrier, the less the distance it takes for that reflected wave to reach your ear drum. And the farther away you are from the barrier, like if you are in a large hall or auditorium, you say something. So the sound it takes longer to travel, and it becomes like kind of deep and rich and resounding, and it has a particular effect in large auditoriums. Now, if you reach a distance far enough, as you say something, the distance will be very far, and the sound is going to take a much longer time to come back to your eardrum. Your eardrum will have stopped vibrating. You say something, and then it hits your eardrum, and that your eardrum stops vibrating. And then the other sound that is reflected comes from a long distance, comes back, and then it hits the eardrum as if it's a completely new sound. Listen and watch these videos, short videos, and that will show you how reverberation occurs and how an echo occurs. So an echo, you hear two completely different sounds. The original sound dies down, the eardrum is no longer vibrating, and then the reflected wave travels back, and then it starts vibrating the eardrum again. So there is a gap. And the definition is really, you need to know how to distinguish between an echo and a reverb. The effects of reverberation. Reverberation, if it is reasonable, it can enhance the sound wave, it can make it nice and rich, and it can enhance your understanding. However, if there's a lot of reverberation, it could cause problems, especially for people who have middle ear infections or people who have hearing loss. They are going to hear the sounds, from multiple sources, and there will be multiple echoes, and reverberations are going to make the sounds garbled and difficult to comprehend, especially in noisy situations. Back to pitch and frequency. We said frequency is the absolute number of vibrations per second. There's no guessing. You have to get a machine to measure frequency. And when you hear something, that frequency of vibration, if you hear it, then you say, oh, it is high, it is low. You kind of guesstimate it, and that becomes the definition of pitch. So pitch is our estimate, is our perception of frequency, and we guess it is high, it is low, and so on. And so naturally, if you say something is a higher frequency, of course, it will also be a higher pitch. Something is lower frequency, also it has to be a lower pitch. Exactly. So pitch is just our subjective estimate of frequency, and frequency is the actual rate of vibration per second. So the faster the rate of vibration, the higher the frequency, or the faster the rate of vibration, the higher the pitch. Frequency is determined by the qualities of the thing or the characteristics of the thing that vibrates. There are three very important characteristics. One is mass, how heavy or how massive something is, and then length, and then tension. Mass. Now, pay attention to this. These are general things that apply to anything. If you have a ruler, if you have a bridge, if you have whatever it is, a branch of a tree, anything. Bigger things, heavier things, massive things, vibrate at a slower rate. So, male's vocal folds. Now I am comparing two different things. I'm comparing a male's vocal fold, for example, and the child's vocal fold. Two. I'm not speaking about my own, just I'm speaking about two different things. The vocal fold of an adult male, the vocal fold of a child. The vocal fold of the adult male is massive. It has a lot of mass in it, and therefore it will vibrate at a slower rate. Therefore, the adult male's voice is lower pitch. So, length. Now remember, I am comparing two different things. I'm emphasizing that because later I am going to speak just about myself. I am the same person. I want to raise my pitch. I want to lower my pitch. But we haven't come there yet. We are speaking now specifically about two different things. So length, if I have a rubber band, that one is, say, 4 inches long, and one is 8 inches long. Guess which one is going to vibrate at a slower rate? Which one is going to have a lower pitch? So the one that is longer, simply when you pluck it, take it away from rest, it's going to travel farther and farther and farther away. You let go, it keeps going back and forth. It takes a long distance to travel. So longer things vibrate at a slower rate because they cover a larger area. So they have a lower pitch. And shorter things, the shorter something is, the faster it can go back and forth, and the higher the pitch. Again, I'm speaking about two different things. Comparing apples and oranges. Tension. The more tense something is, the higher the pitch. The less tense something is, the lower the pitch. And you can try it. Use it. There will be an experiment that we'll do with rubber bands when we tense them or make them, less tense. When we speak about the vocal folds now, it becomes more complicated because the vocal folds are living tissue. And my own vocal fold, I can make it high, I can make it low. So it is going to be more than one factor that will be combining with, with another. So for example, how do you increase tension of the same vocal fold? It is by taking that vocal fold and pulling it, making it longer. And then you say, oh, didn't you say that if you make something longer, it makes it vibrate at a lower pitch? But in that case, when I make it longer, I increase tension, and tension will overcome the effective length. So tension is going to give it that higher pitch. But again, we'll speak about this later. In here, we are comparing two different things. The human range of hearing means it is the range where we can hear a sound. Below this range, we cannot hear the sound. No human being can. Above that range, we cannot hear the sound. No matter what we are, superhuman beings, we can. So there's a range within which we can hear the sound, and that is 20 hertz. That means 20 vibrations per second. If something is vibrating 20 times per second and your hearing is perfect, you can hear that vibration. And then 20,000 vibrations per second. So if something is vibrating at less than 20 times per second, you cannot hear it at all. It does, for us as humans, it doesn't exist. Animals can hear it, but we can't. And then the vibration rate goes up and up and up to 20,000 times per second. If your hearing is perfect, you can hear it. It will be very, very, very faint. And above 20,000 times per second, you cannot hear it at all. Bats, dogs can, but we cannot. So when we say, 20,000 hertz, we could also express it in instead of 20,000, we say 20 kilohertz. A kilohertz is 1,000 hertz. The speech sounds that we have in any language, the best range for speech sounds when we don't have to, the sounds that we don't have to raise as much or to put as much energy into to make them heard, they are the sounds that are between 1,000 hertz and 4,000 hertz. And you can see a table in your book that shows that, page 41. Now the concept of amplitude, we said the maximum point of displacement, which is the end of the peak of the compression, that marks how much energy you have put into that thing that is vibrating. We call this the amplitude. So the amplitude is the maximum degree of maximum point of displacement, and it tells us about the energy that is put. The higher the amplitude is, the greater the amount of energy that is put to make the sound. And we measure amplitude in decibels. So amplitude is similar to loudness, but loudness is our perception of it. Intensity is the amount of energy per unit area that you put in order to make that sound. Intensity. As I raise my voice, how much force do I put to make that sound, to produce that amplitude? It is measured in watts over square meters, or watts divided by square centimeters, depending on the space, on the structures that we use. Loudness. So loudness is the perception of the subjective perception of intensity. When I raise my voice, I say, oh, he is putting a lot of energy to make this voice loud. That is probably, this maybe 20 watts or whatever. So loudness is our subjective feeling or perception of the amount of intensity that is put to produce a wave or to produce a particular amplitude. So it is similar to the difference between pitch and frequency. The tricky thing now is this. For a sound to be doubled in loudness, like you are, say, in your car and listening to the radio, if you want that volume to be twice as loud, you turn the knob once, it becomes twice as loud. However, by doing so, by turning the knob once, it is going to make the energy that is needed to make the volume go from one notch to the other is 10 times more than what was there before. So a sound must be 10 times more intense before it can become twice as loud. So if this, let's say the sound is 1 decibel and you want to make it 2 decibel, you have to put 10 times the amount of energy that you started with. And then if it's 2 decibel and you want to raise it to 3, you have to put 10 times more energy than the 2. So it is called multifactorial, it is added multifactorially. Every time you go up, the numbers could be staggering. So for a sound to be, for example, 3 times as loud, it has to be 100 times more intense than it can be than before. So look at the textbook and see how the numbers, when you go to 5, you speak about millions now. So the intensity units that are used to make a sound that we humans can hear, speech sounds or any sound, the intensity units are 1 trillion intensities. At 1 trillion intensities. So Alexander Graham Bell took these, intensities, and he kind of divided them, put them into 140 steps. So, for example, when you raise the volume from 0 to 1, then you increase by 10, you put, 10 units of energy. Then you go from 1 to 2. You go and say 10 times 10. You get 100 units. And then go one more. Say 100 times 100. And then every time you go, say, so 100 times 100 is 10,000. And then 10,000 times 10,000. And then you just... So, fortunately, every time as we raise the volume once, the energy, the amount of energy is tremendous that is added to make that. So that in effect, it makes us able to stay without being deaf, in other words, that discrepancy. So he takes these numbers, crunches them into 140 units, and we call them the decibel scale, and we used this universally to estimate, to measure sounds. It's a linear scale, and the distance between one unit is the same. In other words, when you say raised by 1 decibel, raise it by 2 decibel, 3, all of these units now are the same. And I don't need to go into deeper details because this is all we need to know for the purposes of the class. So this is an audiogram that is used by audiologists to test, hearing. So the left, the vertical axis is decibel, the loudness, and the horizontal, that is your pitch in terms of wavelength, for example, how long it takes the sound waves. So this is frequency. So frequency, say 120 hertz. And like this is the adult male frequency, for example, 250 hertz, adult female. And then you keep going until 500 hertz, 1000, 2000, 4000, 8000. So you notice between 1000 and 4000, where is it? 4000. Any sound that is in this range here is going to be heard, better than other sounds. It doesn't require as much, energy to be put into it to be made. So you can hear. The other sounds need, you need to put more energy into them to make them loud enough. This gives you, see, on the audiogram, 0 means perfect hearing, factory finish. The baby comes, to life with that perfect hearing. And of course, we lose a lot. We ride cars. Every time we experience a lot of intensive noise and all of this, and our hearing is going to be, less and less, unfortunately, with aging and with the devices you use, iPads and music concerts and all of this noise pollution that we are in is going to affect everyone's hearing. So if you have a perfect hearing at 0 decibel, you can hear an oak leaf as it hits the ground. You can hear a maple leaf or a smaller leaf if that leaf, if it has like 5 hertz, 5 decibels, you can hear it. But it needs to be loud by like, it will be 5 decibels. A fan is the sound of a fan is going to be about 30 decibels. A dog barking, about 70. This is an ancient mobile phone, and they had them in homes. They were so huge. That was very loud too, but luckily we don't have any anymore. A tractor is going to be between 90 and 100. An airplane is about 100 or 110 or 120 hertz. So you notice here that the decibel scale here is inverted. You start with 0, and then as you go down 10 decibels, 20, 30, 40, 50, and you keep going down. Above 0 is -10. -10 doesn't mean that there's no sound. It means that someone's hearing is like almost like super, above average, -10. They can hear things that other people cannot hear. This is not always good. It actually can drive people crazy sometimes, because they can hear everything that, that is not related to what is going on, and that distracts and causes lots and lots of problems. So if someone has, I'm going to show you on the next one, but this means as you go down, and if you need the sound to be raised louder and louder, that means there's a hearing loss. So here, for example, as you go down, I need you to understand the ranges of hearing, normal range and range for mild hearing loss and so on. If someone's hearing is between -10 and 20, and their hearing is for example, is okay here, there's no problem, that is normal hearing. If they need the sound to be raised by 20 decibels, that oak leaf that they used to hear at 0, they can't hear unless you make the sound amplified by 20 decibels. That makes mild hearing loss. So that's mild hearing loss is between 20 decibel and 40 decibel. Always red for right. Red ear is plotted using the red ear, right ear, red color. And then blue is for left ear. So between 40 and 70 decibel, that oak leaf, if it falls and you cannot hear, in order for you to hear it, you have to raise the volume by 40 decibel or 60 or 70. In between this range, that is moderate hearing loss. The person cannot live without a hearing aid or some kind of amplification. 70 to 90 is severe hearing loss. That is very, very significant, and they must use also a hearing aid and other devices. 90 and above is profound. The person cannot hear anything. They basically can feel the vibrations, of the sound by their body, but they can't hear any particular sound. These are the people who are candidates for cochlear implants. So these are the ranges for hearing loss, and I need you to understand, for hearing, so 0, -10 to 20 is normal hearing, and then 20 to 40 is moderate and, mild, and so on. Hearing, if, someone has hearing loss, the effect is tremendous not on the person, just on the person, but the effect on other people. Like say, two people are married, and one person has a significant hearing loss, let's say moderate hearing loss. Every time, let's say the wife says something, the husband says, what? That becomes annoying sometimes. When you keep doing it. And then, not just that, the person who has the hearing loss is going to speak at a loud voice all the time. You'll be next to them and they yell at you. And that also becomes very annoying. So something like this, believe it or not, could break up a relationship. So simply by having a hearing aid, you as an SLP recommending a hearing aid, or going to tell them to go to the audiologist, have a hearing aid, that makes life so peaceful, and just becomes really a great solution. We could, in class, we could go over some of these things, but I would like you to know what an audiogram is. I'd like you to know what is on the vertical axis and what's on the horizontal axis. The horizontal axis has frequencies from 185 to 8,000, because this is 8,000 is where speech sounds between 125 and 8,000. This is where speech sounds, exist. Beyond that, you are gonna speak about sounds, birds and bugs and all kinds of sounds. But for speech purposes, 125 to 8,000 is where all our speech sounds exist. The last thing that we are going to speak about here now is the acoustic reflex. It's also called the middle ear pain threshold. And simply, when the sound reaches 120 or 120 or 130 decibel, it becomes painful. You have a pinch inside of your ear. You have that sharp pain inside of your ear. And the reason is this. Here, this is in the middle ear. This is the eardrum here on this side. There's a bone, malleus. Attached to this bone is the incus. Attached to the incus is the stapes. All of you have had anatomy, I believe. So the stapes is attached to the oval window of the cochlea. So when the sound comes in, the stapes is going to be pushed in to the oval window. And the oval window releases the pressure through the round window, which is below. So the oval window, oval window connects to a chamber filled with fluid, and the fluid has nowhere to go. So if the sound is loud, very, very loud, and the stapes is jammed in, it can explode the round window. It can rupture it, and the fluid in the entire ear cochlea is going to leak out, and it will create a mess. So as a result, there is a mechanism to protect against loud noises. When the sound is loud enough, that muscle here, the muscle is buried inside, this tissue, and this is the tendon of the stapedius. That is called the stapedius muscle. So when the sound is loud at 130, muscle is going to contract. It's going to here. It will contract, it will shorten, and it will take the stapes out, yank it a little bit out of the round oval window, and then it will make the pressure less on the round window, and that will protect. So that is called the acoustic reflex, or the middle ear pain threshold. And the purpose of it is to protect the ear, to protect the cochlea against damage from excessively loud sounds. So you and I would have it at 130 decibel, but for someone who has a history of hearing loss, already there is a lot of damage. The ear cannot afford to have more damage. So the acoustic reflex will trigger at about 90 decibel. It will come faster. It cannot tolerate the sound to be higher, and then the person will start to have pain. So these people are going to have, with hearing loss, they will have what is known as a restricted range, where they cannot, let's say someone is not going to hear at 40 or 50 or 60. They have a hearing loss of 60 decibel. And then you raise your voice a bit, to 70, 75, or 80, and you reach 90, so you are yelling at me, you are hurting my ears. So they can't tolerate much. They say, what? You keep raising your voice, and then once you raise your voice above 90, they start to scream. So they have a restricted range in that regard. So again, we now completed chapter 1, materials, and I hope that you write questions. I hope that you come to class with questions, and so that we can go over the material again and make sure that you understand it perfectly well. Thank you, and we'll see you.